Sometimes it's best to turn off the tele and think more about studying. So, let's spend a few minutes over here in the workshop. And, what is this? What is this? Mini kitty. How can I teach my students if you're sitting in my chair? Come on, off with you. Yes, yes, yes. Hop up now, hop up. Oh, getting a little feisty, eh? Okay. The periodic table of elements. The Mona Lisa of the scientific world. An absolute masterpiece developed in 1860 by Dmitri Mendeleev, a Russian physicist. No, not that chap. That's my great-grandfather, William Olson. The periodic table today contains approximately 118 elements, as you see here. In Mendeleev's time, it was closer to 60. Mendeleev arranged his table by increasing atomic mass. That's the mass number discussed in class by my grandson, Mr. Dietrich. And today's table is arranged by increasing atomic number. And these are a bit different. As you can see here in this element key for silicon. Silicon has 14 protons. And it has a mass of 28.086. Now you're probably asking, well, how many neutrons does it have? It has 14 protons. What about its neutrons? Well, simple enough. We take its mass, 28.086. We round that to 28. We subtract the protons, 14, and therefore we get a total of 14 protons. So let's take a look again at this table. We have 7 periods. 1, 2, 3, 4, 5, 6, 7, descending down the left side. Periods run horizontally across the table. For example, period 1, we have our old friend hydrogen with its 1 proton. We jump across the pond, similar to how I traveled to your country, and arrive at helium. And then we have helium with its 2 protons, and lithium with 3, and so forth. So again, increasing atomic number. How about these vertical groups or families, or columns, if you will? There's a total of 18 of these. If you'll notice, also, similar to the periods, the way they're counted off, the groups are counted in a similar fashion. Group 1, Group 2, 3, 4, 5, 6, 7, all the way across to Group 18. And if you find an element in the same group as another element, there is a little bit of magic that works with that. For example, helium, neon, argon, krypton, xenon, radon, and, oh, mercy, I'm not even going to even try to pronounce that one. These elements all have 8 valence electrons. Do you recall what a valence electron is? Yes, you do. It's the electrons in the outermost energy level. So, because this is group 18, each of these elements in these noble gases, there's a joke there somewhere, each of these elements has 8 valence electrons. Now, if you have 8, you're very happy, very content, and quite full. And therefore, these elements don't want to combine with anything. Helium, neon, argon, they don't want to combine or talk to anybody. Similar to how I was back in my primary school when I chose to focus on academics and not making friends. Group 1 over here is a bit different. Group 1 only has 1 valence electron. Hydrogen, lithium, sodium, potassium, rubidium, and so forth. They all have 1 lonely valence electron. And as you remember in our lesson, they want to have a total of 8. So if you only have 1 valence electron, how will you have a total of 8? Do I go over here to group 7 for these valence electrons? No. We can't do that because if you recall, groups 3 through 12, the transition metals, share inner electrons on their energy levels. So therefore, we have to say group 1 has 1 valence electron, group 2 has 2, group 13 here has 3, 14 has 4, and so forth. So if I am an element, let's say sodium, and I'm in group 1, I have 1 lonely valence electron, but I want to have a total of 8, the maximum number the outermost energy level can hold. So I have to look over here, not to group 7, but to group 17. That's correct. The halogens, which are primarily gases. And you can see any of these elements here have 7 valence electrons and will very easily combine with anything over here in group 1. So back to our friend sodium. As you probably recall, sodium loves to combine with our old friend chlorine. Chlorine has 7 valence electrons. Sodium has only 1. So 1 plus 7, of course, would give us a total of 8. Now, what does sodium and chlorine make when combined? Let's write down these symbols. Na with its 1 valence electron and chlorine with its 7 gives us a total 1 plus 7 equals 8. That's correct. And you'll remember that sodium, chlorine, makes salts. And we all love salt. especially on what you call your French fries. All right, back to our table. And what else can we talk about? Oh, how about the inner transition metals? As you'll notice, these elements look to be a 8th and 9th period, when in fact, they actually get wedged in right here. You see this? 5671. What happened there? 5671, from barium to lutetium. Well, we have to drop down below because, as you'll see, 57 through, all the way across here, 70 wouldn't fit into the periodic table. If we were to place these inner transition elements into the inner transition, or pardon me, the transition metals up here, it would shift everything over, making a complete jumbled mess. So the lanthanides would be placed directly into period 6, all found in group 3. The actinides are very similar. We have 89 here, going across to 102, and these are all found in period 7 between 88, radium, be careful of radium, it's a dangerous, dangerous gas, and lawrencium at 103. So again, 88, 89, all the way across to 102, and then it picks back up at 103. So the periodic table is basically cut up into 3. We have the majority found on this side, if you can all see this kind of an imaginary staircase here. Every element to the left of that are metals. The majority to the right are what we call the non-metals, mostly gases. If might be one liquid here, I believe, and one, maybe 2 solids. And then along the staircase itself, you have a number of what we call metalloids. Now, metals making up the majority are all solids, the good conductors of heat and electricity. They have luster. As you can see, luster is kind of this shiny effect. Luster. They're malleable, which means they can be pounded into shape. And they are ductile, which means they can be stretched into a wire. The non-metals aren't quite like that. Again, mostly gases. You certainly can't pound a gas into shape, and you can't stretch it into a wire. They're all poor conductors of heat and electricity. And for the most part, they are gases, with the exceptions of things like iodine here. And I can find another one here, carbon. Okay, carbon is a brittle solid, not a gas by any means. And finally, the metalloids. Metalloids include things like boron and germanium and antimony and so forth. They have properties of both metals and non-metals. It's kind of confusing. They look like metals. A lot of them are found in your modern day devices, such as my cell phone here. Just joking. But these electrical devices have many what we call semiconductors. Not a good conductor, not a bad conductor, but a semiconductor. If it had a really, really good conductor like copper, it might short out the device, and we wouldn't want that to happen. Okay, so in a nutshell, that's the periodic table today. There will be another lesson or two, because let's face it, there's way too much wonderful things to discuss with this table. And if you'll tune in next time, I will go over some of the other things that you'll need to know for your STAAR test. Some tricks of the trade, shall we say. And until then, cheerio and have a wonderful day. A most excellent cup of tea. Goodbye.